Okay, let's get started. Our next speaker is Dr. Saverio Bolognani. He received his PhD in information engineering from the University of Padova in Italy. After that, he was a postdoc at MIT, and currently he's a senior scientist here in the Automatic Control Lab at ETH Zurich. His research interests include network control systems, power systems, cyber-physical systems, and the intersection of nonlinear optimization with feedback control. Today he's going to talk to us about first and zero-order optimization algorithms as model-free feedback controllers. So, take it away.
Yeah, thanks a lot. Thanks a lot, everybody. And it's very convenient to be at the end of today's line of speakers because you will see some of the things I cover. The discussion we had until now will help, actually, to place them in the right place. So I'll start with a very brief introduction about what's the purpose of what I'm going to present today. And it starts by the following observation, in a way. Among all things that you can call control, automation, one specific automation task is made of the following ingredients that you see here. So imagine that you have a stable or a pre-stabilized nonlinear system, and you're given as a control designer, you're given steady-state specifications. And these steady-state specifications are typically in terms of optimality. It could be yield of a process, it could be economic costs, CO2 emissions, or if you want to include more externalities. The difficulty of the problem is that you have to set multiple constraint inputs, and you need to make sure that some of the states of the system, at least a steady state, satisfy some constraints. Of course, this is made not trivial by the fact that the map from input to output is affected by exogenous factors like disturbances or unknown parameters. Okay? And what you see here on the left has been the driving applications for a while. This is the control room of a power system, right? So I will spend literally one slide or just giving a hint of what it means in that case to do this optimal steady-state regulation. So again, in just less than a minute, the problem that's been given to us was to control, to make sure that the electric state of a part of the transmission grid, in part of France in this case, was safe and maintaining voltage and line limits, even if in the same grid there was a severe connection of new sources of renewable energy. And the new sources of renewable energy are fluctuating, and so you need to respond to what they do. You don't know how they're going to fluctuate in time. And so you need to set a lot of inputs, because these are come in the number of thousands or hundreds, in order to make sure that the state of the grid satisfies what are your specifications. Now, for power system people, this is an optimization problem, right? This is called optimal power flow program, and has been a very classical tool in power systems. I think that the correct way of looking at it is actually that if you just rearrange the arrows from the typically diagram to our textbook control system diagram or block diagram, this is actually a control problem. Like what you have is that you have a steady state power system dynamics, so you have a plant, which is the part that you see here, which is at steady state. You get real-time set points and state estimation, and you need to design something, let's call it a controller or an optimizer, that drives the system to the correct or to the desired steady state. Okay? And from now on, for the rest of today's slides, this is going to be called feedback optimization, right, in this context. So what I'm going to do today is to cover feedback optimization and like a recipe, how we would address this problem of feedback optimization. Actually, not only what has been the result of the work of a number of people. And in particular, I'm going to spend some time on first-order algorithms that can be used to design this controller, and zeroth-order algorithms that can be used for the design of these controllers. And then at the very end, I will mention something that was conveniently placed after the talk that you just listened to. As you can see from the little icon, it's going to be in the direction of games. Okay, so the recipe that I'm going to recommend in these slides for feedback optimization is actually, from the design point of view, pretty simple. It's based on some sort of certainty-equivalence approach. So the idea is that the physical plant that I told you is a nonlinear stable plant is replaced by the algebraic map. So this HUW, it's telling you what are the output of the system given the inputs. Okay? W is just a disturbance that, for most of what we're going to see today is going to be constant, but it's almost a parameter. Now, if one starts from these assumptions and sticks to the idea that you can take this certainty equivalence approach and replace it in an algebraic map, then the steady-state specification is actually an optimization problem, right? So you want to minimize some cost phi of the inputs and of the outputs. You want the y's to be in some feasible region. You want the u to be in some feasible region. And then the algebraic map is going to be just a constraint between input and outputs. How do we design the block on the left here? Well, we take just classical iterative nonlinear optimization algorithms, iterations, right? And we apply them in closed loop with the system. And then we're going to see how many troubles this introduces. Just to clarify how this is new or not new, from an optimization perspective, the idea that you can design or analyze algorithms with the tool of dynamical system is what you have seen in Michael's talk before, right? So this has been done. It's a super interesting topic. There's tools to do that, right? The difference here is that we're not just trying to understand the algorithm through the tools of dynamical systems. This is going to be a dynamical system at the end. This is going to be interconnected with the physics of the system, right? From a control perspective, also it's not new that the fact that some feedback controllers, even very classical ones, can be interpreted as solvers of a specific optimization problem. The problem is that we are given an optimization problem. We can cook one up because it explains our controller. We are given a complex optimization problem. We need to design the controller. And for the first part, we heard enough today. For the second part, this control perspective, I'll give you just a toy example because I think it contains in a minute what's the key idea here. Even such a simple controller as a PI controller can be equally explained, right, as traditionally, from designing it in the frequency domain, or it could be interpreted as a solver for an optimization problem. So this is literally the simplest, or a toy example, the simplest example I could prepare. If, as a control designer, you're given the problem of driving the system to a point where a given output is tracked, a given reference is tracked by the output, and the plant has a linear steady state, and it's pre-stabilized, and you want to do it in the cheapest possible way, then this is an optimization problem. And if you apply some of the iterative algorithms available in textbooks, you get very familiar controllers. Like if you take a dual ascent iteration, so you write down the Lagrangian of the problem, and you alternate between primal minimization and dual ascent, so ascent in the dual variable connected to the tracking constraint, what you get is an integral controller, okay? Just by doing this step literally on paper. And if you do the same with an augmented Lagrangian, where you add a regularization term which vanishes when tracking is achieved, then you get a PI controller, just by rearranging the equation and doing the same step. Of course, this is, again, as I was saying, this is a little bit trivial because this is building on the simplicity and the fact that I can cook up the model or the optimization problem that I want to solve. We need to do it for a more general optimization problem. And just a very quick historical note, the idea that you can take a controller and design first interpret and then design a controller as an iterative algorithm from optimization goes back at least to 25 years ago, where TCP congestion protocols, so the congestion protocols that prevent physical interconnection between machines to be overloaded by data traffic, right, can be actually interpreted as solvers for an optimization problem. So this was a success story in a way, because it was a very compelling explanation of why this method works, even if they have not been originally designed in this sense. So in this case, the inputs would be source and destination data rates between computers. The output would be, how much physical channels are used, like that's something that can be measured through delays or packets dropped or congestion signals. And the optimization problem that you're trying to solve is some network utility maximization. Again, this is one example where saddle flow or a dual optimization algorithm on this optimization problem returns something very similar to the controllers that I use in practice. Okay, so now that I just presented the recipe, then I will present what first-order algorithms can do in this setting. The idea here is that we borrow these first-order algorithms, so algorithms that are driven by gradient, from the standard nonlinear optimization literature, and interpret this as dynamical systems so that we can study their interconnection. And there's a number here which have been studied as dynamical systems very long ago, in a way. Maybe it's worth pointing out the third category that you see here, like acceleration and momentum methods, for which, of course, we just heard some of the most recent understanding of how these are dynamical systems. And saddle point flows that also have been, at least in some properties of their convergence, they've been looked at relatively recently. Okay, so I'm just going to present one example of how a first-order algorithm becomes a controller, and this is the simplest. It's the projected gradient descent, and that's actually the simplest, but also one that we ended up studying and using most often. The idea is that the gradient of the optimization algorithm is available just by chain rule derivation. So, of course, the gradient contains the derivative of the cost function with respect to the input, and the derivative to the cost function with respect to the output, and contains the sensitivities, like the input-output sensitivity of the system. Now, this is actually, if you look at the entire expression here, this is the only piece where the model information enters into play, right? So that's the key point that you need to know about the system, is this relation between the input and the output in a marginal way, like in a local way. The projection here, so here I am writing the algorithm in continuous time, so the projection is exactly what we have seen in at least a couple of talks now. It's the projection of the velocity, right, of this u dot on the tangent cone to the constraints, right? There's no need for convexity in the definition of this one, but this is the velocity that allows you to slide on the constraints to the minimum, right, without violating it. Notice that the projection is not on the set of input constraints, but it's the intersection of the input constraints and the pre-image of the output constraints through the system. So this is constraining the input to be in the set of points which are feasible for input constraints, but also produce feasible outputs. This is so far well defined, although some special care is needed in case these sets are time varying. Mostly because for the existence of these trajectories, so with finite velocity, you need to enforce some additional constraint qualification, like how fast do these sets move or change in time. Now, what's a bit tricky here, and it's been covered a little bit before, is that when you try to implement this one as a discrete time system, you need to tell how this projection is going to actually happen. For two reasons. First, because this is in continuous time and we need to discretize it. And the second, because this requires a piece of model information that we don't want to have, right? So this is the inverse map of the steady-state map of the system. The idea, and I will show you the detail, just the key points or the most important points, is that this can be done with some repeated convex quadratic programming. So the idea is that this continuous time flow can be approximated in discrete time with finite increment, finite steps, where these steps are the following expression, a bit of a proximal sense. So this is the closest direction, the closest step to the gradient descent that we would like to employ, subject to the fact that the next point is going to be feasible according to the input constraints and according to a first-order approximation of the pre-image of the output constraints. Now, this first-order approximation can be obtained by just using sensitivities again, so without further information. And one can prove that with enough regularity and small enough alpha, so alpha is the step length here, one gets global convergence to the set of local minima of the problem for the non-convex problem. Okay, now this was not, of course, the only method. One can use other methods, like you can just take the output constraints and transform it into a penalty function. We heard before that one of the problems there is to make it this steep and at the same time maintain the controller well posed. It's particularly interesting or problematic here because we are typically not allowed to take diminishing step sizes here. We want a controller, right? So we want some persistent control on the system. Saddle flows can be implemented and or converted into controllers for this task. Problem here being, and we're going to see how this is a problem in a couple of slides, exponential stabilities of these flows. And the projected gradient is the one I just showed you, which in practice corresponds to a quadratic programming iteration. Notice that this is also extensions or variations of how this can be discretized actually exist, including making sure that the flow is well defined outside of the feasible region, which in this case is a little bit something I swept a little bit under the rug. In any case, all these methods, which are first-order methods, they require gradient information because of their nature, and because they require gradient information, they require the input-output sensitivities nabla h. So they require this piece of information, and I'm going to come back to that in a second. Okay, now, of course, this was just the recipe to how to design it, right? Not the analysis. In reality, what you are going to do is to interconnect these flows with the physical plant, right? And the physical plant is this nonlinear plant, stable nonlinear plant. So, for example, the optimization flow could be this generalized gradient descent. So this is just gradient descent with a generic gain in front. And the plant dynamics could be an exponentially stable system, right? With the steady state map, of course, corresponding to the one that you used in your design. Now, if you interconnect the two, stability is in general, not surprisingly, not guaranteed, right? Just make the gain larger and larger, and for smaller gains, you get a convergence to the same point where you would converge as an algebraic map. So the dashed line here in red is basically the algorithm, without the physical plant connected, while the rest that you see here is the output and the inner state, in the internal state of the system, of a system that I'm not showing you. You make it larger, it could still be stable, but converge to a different local minimum. You make it even larger, it could become unstable, right? Not surprisingly, right? That's a closed loop of two dynamical systems. The main result, or the way you can actually make sure that this does not happen, is through a single perturbation analysis or timescale separation between these two flows. And I'm just reporting the main result here and then hint at possible variations. But in general, the assumption is that if the system is exponentially stable, so that we also have a Lyapunov function for which you can write bounds on the rate at which the Lyapunov function decreases, and also bounds on the dependence of this Lyapunov function on the input. And if the cost, which in general is a non-convex cost, has compact level set and L-Lipschitz gradient, which is quite reasonable, then all the trajectories converge to solutions, so KKT points of the problem, as long as the gain is smaller than a threshold, and this threshold being a function of this rate of convergence, these Lipschitz constants. Okay? Of course, if the system is faster, then you can be faster with your optimizer. If the cost function is steeper, then you need to be slower, and so on. Okay? At the end, you get really almost one-to-one correspondence between asymptotically stable equilibria of the closed-loop system and strict local minimizers, and strict local minimizer being stable equilibria, so almost a back-and-forth implication. Okay, so this can be extended to projected gradient descent, so the projection doesn't really hurt the analysis, and you get, as I said, a prescription on the global control gain. If you have a preconditioning with a Newton-like preconditioning with the inverse of the Hessian, you get some invariance under scaling, okay? And in the case of saddle flow, the tricky part it would be that the flow needs to be exponentially stable, right? Which for convex problems is something that's been looked into only quite recently. In general, this is also telling you what you cannot do. Like some acceleration gradient methods cannot be used. The one, for example, where the damping term decreases in time. Some subgradient methods cannot be used and in fact destabilize the system because of the lack of Lipschitz gradient of the cost function. Okay, and the more general case, and here I'm not going into the details here, is going to be a for generical or for general optimization dynamics, including possibly memory, so including Seidel flows, as long as you know the exponential stabilities of these flows. Okay, so the take-home message for the first part here is that if the first-order model of the system is available, so these input-output sensitivities, and if the system is fast stable, then first of all, the gradient or Seidel flow trajectory are valid closed-loop trajectories. So that's what you could try to achieve, right, from the closed-loop system to see the gradient flow happening in the system. You can just take first-order optimization methods and use them as optimizing controllers. This control design is almost model-free, and the star here comes from these input-output sensitivities, right? So there are applications, including the power system application that I've told you about, where these sensitivities are easy to estimate, and they are relatively constant, and they come from parameters of the system that are not subject to many changes in time. And so I would call it almost model-free, but we're going to see in the next part that this is not a general statement. Like for other problems, knowing the sensitivities is a tricky business. And the stability of the closed-loop system can be guaranteed with minimal model information, like in particular by timescale separation, which is relatively agnostic of the details of the dynamics of the system, as long as you can estimate those quantities and that threshold. Okay, so time to move to zeroth-order algorithms. When did they start? That I know more or less.
20 more minutes.
How much? 20. Okay, perfect. So in zeroth-order algorithms are algorithms where you don't use the gradient. And when is this the case? So I'll just bring one example as industrial as the previous example, just to give an idea. When you operate a compressor, right, typically you want to operate at high efficiency. And typically what's given to you is something like this, right? So what you get is a map that, depending on what you pick, input and outputs, gives you some efficiency. Now, measuring the efficiency is typically relatively easy in the sense that by looking at the input and output power to these machines, you know how much is wasted. Knowing the gradient of this cost function is, well, if you knew the gradient, let's say, the problem would become a little bit trivial, because the gradient is literally telling you where the peak is, right? And so there are these applications where, call it samples or Bandit or Oracle, but there is information about the value of the cost function. There's not much information about how or in which direction to move in order to improve this value. Okay? And now we can take two possible directions here. One is to stick with first-order algorithms, and in that case, you need to somehow estimate these sensitivities, right? So these nabla H. Okay. You can use a recursive least square. That's something we have attempted. There's been some recent work about using shape-constrained Gaussian processes because the derivative being a Gaussian process allows you to, for example, enforce convexity. There's been some recent efforts to use data-driven or behavioral systems theory to estimate these sensitivities, right, from data. But what I'm going to cover today is a slightly different direction, in which instead of trying to estimate these sensitivities and build the gradient, we try to use to really do optimization without the gradient. And this comes from a number of tools, which I'm going to review very, very quickly, or just mention, rather, which are, for example, extremum seeking, reinforcement learning, zeroth-order optimization. As you see, I have a preferred one. So, in general, these tools, they need somehow to return at the same direction without first-order information. So some magic needs to happen in these tools so that this descent direction is revealed. In extremum seeking, the key idea is that a perturbation signal is injected. So you see, for example, a sinusoidal signal is summed to the input, and is also used to demodulate the output. So the gradient, the cost function, is then returned by the oracle, by the system, and then remultiplied by the same perturbation signal. You can easily see that if you integrate or average this one over a period, then what doesn't vanish here is a term which is an approximation of the gradient. Okay, so somehow from only measurement of the output of the system, you get, or of the value of the cost function, you get an estimate of the descent direction. So something happens here, like there's this trick that allows you not to need sensitivity information. In reinforcement learning, at least in the policy gradient kind of approach to reinforcement learning, also the trick is that somehow your sensitivities or the direction in which changing your parameters theta would influence your reward function somehow does not require you to know the gradient of the value of a state action pair as a function of these parameters, right? It only requires you to be able to average it, right? And so how you're going to do that, that depends on the many methods available. But in general, once you start having samples, then you can also approximate this reward. And you don't need the sensitivities, at least not, you don't see it. Like implicitly something is happening that returns you the sensitivities, but you never have them in your algorithm. In zeroth order optimization, you typically get 1 point, 2 points, or many points, function evaluations, and from those, you try to extract a descent direction. Typically, there's some randomization happening, so this descent direction is then fed into a stochastic gradient descent. If you look at the available unbiased gradient estimator for zeroth order optimization, it's actually not trivial to find one which works well in closely with a system. And I'm going to tell you why by just looking at 3 of them. First of all, they all rely, in general, on having an exploration parameter. So adding a little perturbation to your input so that you see where the cost function is increasing or decreasing. And this perturbation, let's suppose that for all these methods, come from the normal distribution. Now, a relatively classical tool is to say, let's estimate the gradient from one function evaluation, which seems like magic. But actually, if you take the expectation of this 1 point evaluation of the cost function, what you get is in fact an unbiased estimator of the gradient. The problem with this estimator is that the variance of this estimation is very large. And so when you feed this into a stochastic gradient descent, the convergence rate is typically very, very poor. Okay? Even if you assume some regularity or smoothness. What works much better in zeroth order optimization is to apply 2 point gradient estimators. So by evaluating the cost function in 2 points, what you get is still an unbiased estimator. Notice that when you take the expectation of this one, the part on the right here is inconsequential, right? Because it vanishes for a zero mean V, perturbation V, right? But it decreases the variance of the estimator. Problem for feedback optimization is that this requires multiple oracle calls, right? At least 2, right? It could be extended to more than 2. And only very recently, there's been a zeroth order estimator of the gradient, unbiased estimator of the gradient has been proposed that uses streaming data. So this is an estimator where, very similar to the 2 point estimator, but where the second evaluation is actually at the previous data sample, right? Is at the UK-1 and VK-1. So we are reusing the points in your iteration, in your time series, to construct this estimator. Now, in general, this is not unbiased, but once it's connected to the way in which you update your inputs is a gradient descent rule, then this is actually an unbiased gradient estimator, and it has the small variance of the 2 point estimator. Okay? So you can then feed this estimate here of the gradient to a stochastic gradient descent rule. Now, to be precise, this is not an estimator of the gradient of the cost function. It's an estimator of the smoothed version of the cost function, where the smoothed version is the Gaussian blur in image processing. So it's the processing where every point is replaced by the sampled version of that point according to a Gaussian sampling around that point. Okay, so that's how the interconnection would look like. So the interconnection would look like the physical plant that I described before. And you see the assumptions here are kind of similar. We want this plant to be exponentially stable. Notice that now we are in discrete time here because the zeroth order method really needs to be defined in discrete time. We need this physical plane to have a unique steady state map. Okay, that's not that was common before as well. And being Lipschitz continuous, also the output function. The optimization controller will look like this, right? So it has an explanation signal, which enters here in the input, and it's sampled from the Gaussian distribution. It has measurements, of course. It has this cost oracle, so the cost function in UK and Y, k plus 1. Each cost oracle is used twice, right? You see that it appears here and then here again. And the descent direction that you build with this estimator here is going to be the one-point residual feedback gradient estimator that I showed you before, and is going to be fed into a stochastic gradient descent. Now, what you can show is that you can do this closed-loop stability analysis for this method as well. And here, there's no need to parse this amount of math in this slide, but I will point to a couple of things. So if maybe what's important is that if P is the input dimension, and mu is the rate of convergence of the plant, then you're typically also given epsilon. Epsilon is the precision of that Gaussian approximation, the ETH one here, right? And this dictates a size of the perturbation signal, okay? That's just, it's not part of the result. Now, once you're given this, you're given the rate of convergence and you're giving epsilon, then these results prescribes a maximum gain of the stochastic gradient descent that ensures that the regret, so the norm of the cost, norm of the gradient of the cost function evaluated over a time window for you to design of size t, is order of these parameters. And you can see, of course, this is going to 0 with increasing t. And for fast systems in which mu is small or is going to 0, so the rate of convergence of the plant is faster, then it simplifies to something which is a little bit more readable. The gain of the stochastic gradient descent is bounded by the precision that you want to achieve and the dimension of the system, and the regret is bounded by 1 over square root of t, which is actually what you would probably hope from the gradient descent anyway. And it doesn't really grow too quickly with the input dimension. The rest that you see here, the ETH star and the rho, there's expression for that, right? It's not just not here, but there can be computed. Okay, the proof, I will only sketch it super quickly. It actually requires to study the two interconnection, and so quite similar to the other proof, it requires you to have a Lyapunov function for the physical system, and it requires to study the interconnection of this Lyapunov function, which is contractive, of course, with the rate mu, but is also driven by the estimate of the gradients, and this recursive expression for the size of the gradients, which is also contractive, but is driven by the fact that the oracle is not measuring the system at steady state, but is measuring a transient output. Okay. Now, if you combine these, then you get, if you want to make the interconnection of the two stable, then you get that condition of the different parameters here, which return what you have seen before. And if you look at numerical experiments, here we made a numerical experiment which is a little bit outside of the theory, in the sense that the cost function that we're using here is actually non-smooth. There is an L1 regularizer. So the first order method that we're applying here cannot be the one I showed you before with first order information. So we use the approximal gradient because this regularization here can just be replaced by this soft thresholding. And instead, for the zeroth order proximal gradient, we did the same, but we just fed this estimate into a proximal gradient step instead of the stochastic gradient descent. And what you see is what we were kind of hoping for. So the first order, the blue one, is the first order algorithm, converges quickly and to the minimizer, to the local minimum. The zeroth order trajectory, which is the purple one, converges slower, and it has a residual perturbation effect that's expected. Interestingly, the first order method with a 5% error in the sensitivities will converge fast, but will converge to an approximate minimizer, right? So that's why, in light of these results, I would maybe call this one the model-free feedback optimization, and the first one a little bit model-light, maybe. Okay, so the take-home message for this part is that if you have function evaluation, so a zeroth-order oracle, and the system is fast stable, then you can use one-point gradient estimate as an optimization routine or iteration. The gradient estimate that you get is an unbiased estimate and is a valid direction for stochastic gradient descent, and you get this 1 over square root of t regret from this model-free controller. And as before, the stability can be guaranteed with minimal model information, which is as I said, as long as you can bound this quantity properly. And for this, there's this archive version that has been just posted. The last thing I want to just mention, and it's not going to be a presentation of any or many results, but more like the direction which we're currently exploring, is the extension to this to a setup where you're not doing optimization, but you are considering a multi-agent world. And even in the power system case, this is actually what's happening. So Switzerland or France or whatever country we're trying to control the optimal power flow before is not an island, right? So it receives the decision or is affected by the decisions of the rest of the networks that are connected to the same to their borders. Now, what you get in this point is multiple decision makers with individual costs, independent inputs, but the coupling of the inputs decision in a game theory setting. And here I can really use what has been said in the last presentation, and be a bit quicker here. The solution concept that one adopts in this case is Nash equilibrium, or in this particular case, a generalized Nash equilibrium because we allow the set of feasible actions to also depend on the actions of the other players. For the rest, it's kind of similar as before. You have an output that is also a function of the other agent's decision, of course, and a cost function, which is a function of your own decision and of this output. Now, if we have a convex and differentiable Ji, so this cost for the individual, phi I, sorry for the typo, then this Nash equilibrium is the variational inequality that you've seen before, right? So this pseudo-gradient mapping of the game needs to be pointing inward in the set of feasible decisions, right? So that's why you have that's the alternative. We heard about this fixed point definition of the Nash equilibrium and this geometric one. So that's the one where you want the pseudo-gradient mapping to point inward in the set of feasible actions. And so if you look at this one, actually, it turns out that what we've been derived before, which was more or less trying to converge, at least the first-order algorithms part, was trying to converge to points which satisfy this one for a gradient map, so local minimum of a cost function, can be actually used to some extent also for this different variational inequality where you're actually working with a Nash equilibrium condition. And so what you get is a equilibrium-seeking algorithm in close loop with the physical system. The equilibrium-seeking algorithm could be one of the one that we have seen before, but it could be, the best response iteration, right, given the output of the others. Differently from before, that's a best response, but when you don't know what the others are doing, you know the output of the physical system affected by the others. And so what you typically get in this iteration is a transient output of the system, right? And which makes the analysis a little bit more involved. The result, which I'm only stating in words here, but there's a reprint by Giuseppe and Dominic and others, is that if you have similar assumptions, so exponential stability of the plant, linear convergence of these iterations, and strong monotonicity of the game map, then you can achieve the stability of the interconnection as long as the sampling times are sufficiently long, and in some cases as long as if you are allowed to filter these iterations. So instead of applying the best response, you might be forced to apply a filtered version of that best response. And what you get is an input-to-state kind of result, where the state of the system is input-to-state stable with respect to the disturbance, the W's that enter here, in particular to the rate of change, to the infinity norm of the rate of change of these disturbances. Okay, so I will then conclude. I mean, this is the example application that where we try to apply this feedback equilibrium seeking idea. That's a swarm of wireless vehicles that can communicate to the neighbors, but with a low-range wireless communication. Following the entire paradigm I just told you about, each of these has been pre-stabilized locally by a local MPC, and their cost is the signal-to-noise ratio to their neighbors, right? So there is a communication path they're trying to establish, and they need to dispose themselves in a situation or in a configuration that allows the best communication. So if the 2 points are here and here, what they would have to do is to kind of move into this direction. What makes it trickier is that they have their own dynamics, right? So you're iterating their set points as you're getting information from what they're doing, and on a local base. So they're only talking to their neighbors. And I just conclude with a simulation that Giuseppe kindly provided. That's what the kind of BA you would observe, right? Even in case of a time-varying game that they are trying to solve, they would converge, they would try to seek the equilibrium which is the solution of that variation inequality, which satisfies this Nash equilibrium for the game they are solving. Okay, so with this one, I will conclude. I'd like to thank you for your attention, and also thank you all the people that I've mentioned throughout the slides because this is joint work of quite a few people here at IFA. Thank you.
Thank you, Saverio. Great talk. Do you have any questions from the audience? In keeping with local custom, maybe from Roy? I'm joking.
But there's Bashar as well.
Sorry.
Go for it.
I may go for the first question. The question is on the feasibility of your algorithm. The thing is, if I did not understand wrongly, you actually have an explicitly known constraint. Even for the first order, you seems to have a map from your input to output, explicitly known map, and I think it's y to the minus of yes. Yeah, that one, h to the power of -1.
Right.
So you assume you know it?
No.
No?
In the sense that we need to project on this set here. Now, we need to project not the point, but in a way the velocity. So what you see in the next one is that, so imagine that this is the output constraint,
yes.
right? And the one where we are projecting our increment in the input is this set here. Now, this set here contains 2 pieces of information. Well, it's a Taylor expansion of the constraints. Okay. But the key point is that it's truncated at the first order. So the nabla h is just the sensitivities.
Okay.
You don't need to invert the h minus 1 because this approximation is centered in y, which you measure.
Okay, cool.
So that's why you don't need to compute explicitly h minus 1 of the set. You just need locally, in the point that is given to you from the measurement, to compute the shape of the gradient in that point, or the shape of the constraint in that point, as a linear approximation.
Yeah. Then in this case, if you do this in a 0th order way, and how can you make sure that the constraint is satisfied?
For the 0th order one.
The 0th order, yes.
Yeah. So for the 0th order one, there's 2 things you need to change in order to make it work in that case. The first one is that this perturbation cannot be a normal distribution. You can make it small, but just mathematically speaking, that would have an unbounded support. You can rephrase or rederive the same result with a uniform distribution. So that you can exchange some slack with the exploration. Okay. If there's an input constraint that you're not aware of, and that is taken care of by the physical system, like you send a set point and it's tracked up to some level, and then is not tracked anymore above some limit, saturation, that's actually not a problem, like in the sense that we allow non-smooth cost functions. And that would just be an H, not smooth H. So that would be actually an input-output function, which actually is saturated there. If you have a constraint on the inputs that is actually coupling inputs and you want to enforce, then we need to know it, and you're right. And in that case, we need to incorporate it into the gradient rule. And we have a result where we employ something different from the gradient, from the stochastic gradient descent. But that's the only case where, so you're enforcing a constraint that is not inherent in the system, but is given to you as a specification. In that case, yes, that requires some extra care. Yes.
Like if you have something like you have a constraint on the output, but you don't quite know the map from the input, then in this case, it's not a specification anymore.
No.
Do you think it's very important to?
Sure, it's a bit application dependent. In this case, that would become, I would include it as, for example, as the penalty function, right?
Okay.
Which I understand might come with some, may introduce some trouble when you're doing zeroth-order optimization with the penalty function, but that's what we currently have.
Okay. Yeah, I think if you only care about the feasibility of your, when you get steady state, then I think it's not a big problem.
Yeah.
Okay, thanks.
Thank you.
With Nash equilibrium seeking, using memory sometimes helps in speeding up convergence, like integral feedback.
Okay.
Have you looked into that or incorporated it into the algorithm?
No, right now this best response iteration is just a map, which we allow to be dynamic only in the sense that we might have u at time t+1 being a convex combination of the previous u and the new map. Okay, so we're not allowed the flexibility of designing a higher order map of this kind. But that's a great suggestion.
I mean,
sure.
There's evidence that
would
actually
help.
helps considerably. Both not only speeding up convergence, but also in cases where it doesn't converge, bringing in memory will assure convergence.
Oh, okay, so qualitatively introducing convergence
Right.
where it's okay.
Yeah.
Thanks.
So, thanks for the nice presentation. Really very interesting, and I like the discussion about this zeroth order approach and perturbation with the Gaussian. It reminds of some completely different optimization algorithms, evolutionary algorithms, which are also based on Gaussian perturbations and then different mechanisms. One discussion which I think is always a little bit underrepresented, what happens if you are trying to optimize noisy functions? Because then obviously a lot of robustness of gradient-based estimations breaks down drastically, and then I mean something zeroth order can be more robust, and it would be really interesting to learn how much more robust, how much. I mean, you could also say you add a few evaluations to increase robustness. What is the trade-off? These discussions. That's a very interesting thing to learn.
Yeah, that's a great recommendation, and it's yes, it's a great comment. Like in these methods, so in practice, what we have observed, for example, for the first-order algorithms, is that because we are still so there is some filtering happening anyway, in the sense that if you see here. I don't know, even something as simple as this one. So whatever estimate you're trying to build of your gradient is fed into an integrator for the input. Now, this means that if I put in front a gain which is small enough, I'm also filtering out noise at the cost of less tracking performance. Okay, but that's kind of the trivial solution to your question. Like, you could be slow enough that you don't suffer the noise. In terms of the estimation here, we haven't looked into, for the zeroth order, we haven't looked into that for now. I agree.
Okay. With that, sorry, I don't think we have time for any more questions because we've got to start the panel discussion, so I apologize for that. But I'd like to thank Saverio for an excellent talk and invite the speakers to come up and sit in the panel.